Hello, in this video we are going to solve example based on transient analysis and type of example is find initial conditions. Let's solve. Before that we should know steps to evaluate initial condition. First, wherever there is a resistor, keep as it is in the network. Next step is draw equivalent circuit at t is equal to 0 minus. That means just before switching action takes place. First, find the current through the inductor and voltage across capacitor at t is equal to 0 minus. Then, draw the equivalent circuit at t is equal to 0 plus. That is immediately after switching action takes place. In that case, replace all the inductor with the open circuit or current source depending upon initial condition. If initial condition 0, then open circuit. If initial current is there, then represent that initial current as a current source. Then replace all the capacitor by short circuit or voltage source. If initial conditions are 0, then short circuit. If some initial voltage is there, then by voltage source. So like this, draw the equivalent circuit at t is equal to 0 plus. Then in that step, you can find initial voltage or current in the network. Then next step is draw the equivalent network for t greater than 0. So initial conditions, that is di by dt, dv by dt, d square I by dt square, d square v by dt square at t is equal to 0 plus are determined by writing integral differential equation for the network for t greater than 0. And how you will get this integral differential equation? By applying KVL or KCL to the network for t greater than 0. Let's solve some example. First example, in the following network, the switch is closed at t is equal to 0 with capacitor uncharged, means initial conditions are 0. Find the value for I di by dt d square I by dt square at t is equal to 0 plus. It can be given as a I of 0 plus, di by dt 0 plus, or t is equal to 0 plus can be represented separately. So all this means we have to find I of 0 plus, d by dt of I of plus, d square I by dt square at t is equal to 0 plus. And the given network is this one. And what is this I? First check whether this I is any element current or any loop current. So this I of t is nothing but this loop current. So we have to find this I of t for initial conditions at t is equal to 0 plus. Now here it is given capacitor is uncharged. That means before closing the switch, charge developed across capacitor is 0. That's why our first step to draw the equivalent circuit at t is equal to 0 minus before switching action takes place. Find the current flowing through the inductor and voltage across capacitor. Here only capacitor is there, and what is the voltage? Vc of 0 minus is 0. So we'll represent this capacitor voltage 0, means the voltage at this plate and this plate is same. So it will be represented as a short circuit and your switch is open at t is equal to 0 minus. So what will be the loop current? As there is no path to flow the current because of this switch open, I of 0 minus, that is the loop current, is 0. Now you have to draw next step circuit at t is equal to 0 plus immediately after switching. What is the status of inductor and capacitor? Replace all the inductor with open circuit or current source and replace all the capacitor by short circuit or voltage source depending upon initial conditions. Always remember inductor and capacitor status at t is equal to 0 minus and t is equal to 0 plus remains same. That's why how you have represented capacitor at t is equal to 0 minus, same you have to represent at t is equal to 0 plus. Voltage across capacitor before switching and after switching remains same. It is 0, it is given. So we'll represent capacitor by short circuit and at t is equal to 0 our switch is also closed. We want to find loop current at t is equal to 0 plus. This I of 0 plus is nothing but 100 divided by 1000, that is 0.1, unit is ampere. So this is our loop current which we want to find at t is equal to 0 plus. Next step is draw the equivalent circuit for t greater than 0, and the equivalent circuit is, now this is important, our switch is already closed. How to represent capacitor? It depends upon initial conditions. If the initial voltage V of 0 minus or V of 0 plus is 0, only we will draw capacitor. If some initial voltage is there, we have to connect voltage source of that value in series with capacitor. But in our case, initial voltage across capacitor is 0. So only capacitor we need to draw. Now at this point, we need to apply KVL. Apply KVL. So this 100, this is 1 microfarad capacitor value. Apply KVL. 100 minus 1000 I of t minus voltage across capacitor equation we know. 1 by C integration 0 to t I of t dt. Plus one more term was there, V of 0 plus. But V of 0 plus is 0. Initial conditions are 0. So there is no need to write. Only 1 upon C 0 to t I of t dt is equal to 0. Now what we want to find? We want to find di by dt, t square I by dt square. But from this equation we cannot find it. So now differentiate this equation with respect to t. Just put the value of c. Same equation here. Now differentiate this equation with respect to t to get di by dt. Differentiation of constant 0. Differentiation of this I of t minus 1000 at it is and di by dt minus 1 by c at it is and differentiation of this integration term. Now differentiation and integration opposite operations, it will cancel each other and we will get minus 1000 di by dt minus 1 by c I of t is equal to 0. Now we want to find this di by dt at t is equal to 0 plus. So put t is equal to 0 plus in this equation. Minus 1000 di by dt at t is equal to 0 plus minus 1 by c I of 0 plus is equal to 0. We already know I of 0 plus. We calculated in the second step, that is equivalent circuit at t is equal to 0 plus. I of 0 plus is 0.1. So put it here. We'll take this term to the RHS. It becomes positive. 1 upon 1 into 10 raised to minus 6, capacitor value 1 microfarad into I of 0 plus. Now take this minus 1000 to the RHS so that we can calculate di by dt at t is equal to 0 plus. So 10 raised to minus 6 will take into the numerator. It becomes positive. This minus 1000 into I of 0 plus is 0.1. So calculate it. It becomes like this one and it is now minus 100 ampere per second. Unit is ampere per second. This is di by dt. We are interested in a d square I by dt square also. So what you have to do? Again, we can differentiate this first equation. So this is our second answer. This first equation, we'll write it again here and differentiate this with respect to t to get d square I by dt square. Minus 1000. Differentiation of this term is d square I by dt square minus 1 upon 1 into 10 raised to minus 6 into differentiation of I of t is di by dt is equal to 0. We want d square I by dt square and that we got in this equation. So here we will put t is equal to 0 plus. We know di by dt at t is equal to 0 plus, which we calculated, minus 100 ampere per second. We'll put that. So d square I by dt square at t is equal to 0 plus minus 1 upon 10 raised to minus 6, and this value is minus 100 is equal to 0. Now solve this for d square I by dt square. So this term will take to the RHS and this minus 1000 also, and here solve this. What you will get, this will get cancelled and this term will come here. So it is 10 raised to 5, minus minus become positive. Unit is, current unit is ampere, and for this t, second square, ampere per second square. So this is our d square I by dt square at t is equal to 0 plus 10 raised to 5 ampere per second square. So we got our three answers: I of 0 plus di by dt 0 plus d square I by dt square. We will summarize our steps here to find the initial condition. First step is draw the equivalent circuit at t is equal to 0 minus. While representing inductor or capacitor, you need to take care to check the initial condition. If initial conditions are 0, capacitor voltage is 0 means short circuit, inductor current is 0, that means open circuit. If initial charge is there, that means capacitor has some constant voltage, so voltage source. Inductor has some constant current, so represent it as a current source. Then draw the equivalent circuit at t is equal to 0 plus. Remember, whatever state of inductor and capacitor at t is equal to 0 minus, it remains same at t is equal to 0 plus. Then check whether you want to find loop current or node voltage or any voltage across any particular element. Find that at t is equal to 0 plus. Then third step is draw the equivalent circuit at t greater than 0. So at this point, you need to apply KVL or KCL depending upon what you want to find. If you want to find loop current, apply KVL. If you want to find node voltage, apply KCL. So here in our example, we did for the loop current. That's why we applied KVL. So whenever you are applying KVL or KCL at this stage, you will get integral differential equation. In this integral differential equation, if you want to find di by dt, if it is available, put t is equal to 0 plus. If it is not available, again differentiate that equation with respect to t and get your required value. Then for second order, again differentiate the equation with respect to t and then put t is equal to 0 plus to get that second order value. So like this, these are the three steps to find the initial conditions in a transient analysis. Thank you.